Okay, okay. Well, welcome back. So today there's the third lecture of this. So this is
okay, so I begin just by finishing the discussion about periodic waves. So the first thing I should do is just state some theorem, whatever we do now. The notion of stability that is involved, I already kind of started to introduce the fact that I would need some phase, but the phase will be time and space dependent. Because of that, because it's space will be stability, just to remind that you have some dependence on the spatial variable. It's not like orbital stability where it's just something depending on time. And I've already motivated the fact that it was more or less coming from the fact that you have plenty of position to synchronize, but it's also coming from the fact that you have so many parameters that you can move a bit the shape, and this will change the velocity. Okay, so if you do this locally, if you start changing the velocity locally, there will be some strong motion. So the fact that the speed depends on this m parameter that we've seen yesterday, we have it is actually responsible for the fact that you need to do something in a special way. Okay. Before giving a statement, I'd like to point out that what I say here, the fact that you have extra parameters coming from the conservation laws. Okay, my system is only made of conservation laws, but each conservation law is adding one parameter, but by adding constant of integration in the profile equation, like the Q parameter from yesterday that was dealing with the M parameter. So if I have no conservation law in the system, let's say reaction diffusion or something like this, then I will not have these extra parameters. And the issue I was mentioning about needing a phase that is depending on space is not true anymore. So the case is simpler, and it has been done way before. So I'd like to at least point to the some reference for that. No conservation law. It has been first. Okay. First proof by Guido Schneider, 96. Okay, so there's one word about the proof. It uses normalization. So the proof is actually beautiful. It's the very first one, but it's way too complicated for the problem. So that's really not the right. Incredibly beautiful, but not good. In a way, almost useless now. But it was the first one. It happened quite often. Like the first one you solve a problem, you're doing it in a very way, not the right. And normalization is coming back from the fact that in this case, in a way, the large time dynamics is described by Burgers, and Burgers ends up in a self-similar. So, because you have a self-similarity, you can try to analyze long time by doing a normalization. So scaling the problem. We have started by revisiting this thing. Okay, some So if you want to actually look at the details of what I'm discussing now, I recommend that you start by looking at this paper. So it's analyzing the simpler case with tools that we are using in the general case. Well, we make this mostly for practice, okay, just to see that in the easy case, you get a short proof, simple result. Right now, so. just after. Yeah. I will do the assumption corresponding to saying that I have a specific kind of stability, but I have some constraints. Okay, so the constraint I've already mentioned. But we know that 0 is in the spectrum. For C equals 0 with some multiplicity. And we also know that when you, because it's the problem is actually depending on C, when you move LC, this will be broken and moving. And the best you can expect is that it will settle in the image on the good side of the measure axis. So something like this. And the rest I don't care. It's far away from the measure axis. It gets exponential decay. But I'm not the rest, but the best we can expect is something like this. So I will assume that we have something like this. And maybe I should also say that I'm only in this course I'm showing how to go from spectral to nonlinear. But of course, we've also made plenty of studies of checking in some specific equation the existence, the stability, proving things. But okay, we do it separately because okay, it's a separate problem in a way. But the assumption I'm making now are the right one, okay, the one we are able to prove in general. So let's do an assumption corresponding to this picture. This means that the spectrum at the left of the measure axis, except for 0. LC. Going away from the measure axis when you move C. Okay, so at C equals 0, you reach 0, but afterward you have kind of different behavior for the real part. Also assume that 0 has minimal multiplicity for L0. The last thing is the last thing I will show you in the proof. I don't want to take it precisely to stay, but assume that we have different velocities. Yeah, this will come as translation. So it's sitting in this way. This is also, it would be easier to explain with modulation system. There's a way to guess what should be the large time dynamics. We actually prove what is the large time dynamics. I'm not discussing it here, but we have a complete description of what is happening in large time. Meaning that essentially we have a complete description of what is the phase doing in time and space. Because depending on time and space, it should be kind of solving a system of PDEs. So we have this system, and these are like characteristics for the system. We'll see the same. Then, I can do that. Time space. I'm adjusting position in space by something that's depending on time. For this to be meaningful, I need also this object to be reasonable. Okay, so this is non-decaying, otherwise I will not need it. But its derivative will be decaying. So that's the bit as for the ODs periodic solution. You have a phase that is converging to some constant, so it's not decaying, but its time derivative is decaying. Yeah, that's the same. Time and space derivative of time. Decaying like the heat from the benefit. More or less to the fact that the derivatives decay, that locally you will become inconstant. But the constant depends on where you are on space. Not like a uniform constant that you can remove. Something that depends locally. Okay. Sure. Really is kind of the same as possible. Really is.
No, I'm sorry, I don't recall what is E.
E0 you mean here? Or the equation? The equation is the equation in a moving frame with scale variable. That's just a way to make U bar stationary for the equation. So the equation was I can rewrite. Okay. E scale bar.
Okay.
There's the equation in the frame that makes my wave stationary in time and also period one. Okay. Otherwise, I would need to remove some minus CT at different places. It's just a okay, so the unknown would be multiply and then some shape deformation, and it's obtained essentially as well. Right? Maybe I should say that there are plenty of ways to fail at the end. There are plenty of things that could look a bit the same, but not exactly. But we get into trouble. But here, one of the good things is that since psi and bit should be unknowns in the end, they should be defined on the same time and space thing. Okay, so then when you write the equation, then it's single equation, everything evaluated at the same. Okay, this is why I'm putting the psi here and not there. So, also, some other thing is that when I plug this into the equation, the psi will mostly appear because so it's like in a change of variable. So it will appear because the change of variable doesn't commute with derivative. Okay, it will appear because of commutators between derivative and change of variable. And because of that, the only thing that will appear in the equation are derivative of the phase. This is very important because the phase is not decaying, the derivatives are. Okay, so the good thing is that only this way only derivatives appear, and so you can close things with quadratic terms that are reciprocal decaying, and everything is fine. Yes.
Reaction. This is called a reaction.
No, it was a Power system of conservation laws.
Okay.
Exactly. Again, one more comment on that, at the linear level, where you see that you don't have, when you don't have these n parameters, you don't have a Jordan block. So the stability properties are better. Okay, if I had no Jordan block, I would not need a phase. Maybe I would need, okay, I would need a phase in the proof, but okay, to see that again it decays fast enough so that I don't need it. Okay, so I'm plugging this into the equation, and then I get an equation that is like at the linear level. This is the linear part of the equation. It has this good shape, but it's the same L, but acting with on someone that I need to split in L. Then you add some quadratic terms. And then when I say this, I mean also on their derivatives. Quadratic in this case. Actually, a small remark. Besides, I start with an equation that is parabolic semi-linear. But the change of variable more or less make it quasi-linear. And here I have terms that are too many derivatives to be treated in a UML form. I need to do something. Okay. Because I will get the psi will appear in front of the dx squared.
Ah, okay.
Because my unknown are psi and d.
Okay, but it's the lines on C side of it.
Yeah, the unknown are psi and d, and I'm saying that if I just look at the quadratic term, they involve the maximum number of derivatives. That's the two derivatives. So in this part, there are things that contains two derivatives of d multiplied by something. Okay, and if it's not okay, maybe it's not clear right now, but if you put this number of derivatives in a fixed point, that doesn't work because you will need to integrate to 1 over t minus s. That's too much. That's exactly what you cannot do. Then the rest is the same. What you should be able to do is split the sum equal to and so on. Time should decay, the continue as I need to first be able to do. Once I've done that, I can use it in the UML formula as before. I write the UML formula, there's a semi-grouping factor of everything in the UML formula. I split the UML formula in two parts. So this part is good, it's decaying, I'm putting it in V. This part is not so good, but it's like a U prime times something. So I can put it in psi times U prime. And then I forget about the U prime. And I get psi, which is this guy. So psi is not decaying, but it's derivative R, because I'm okay, it's more or less a constraint in my construction at the linear level. This is what I need to do at the linear level. Then use it in the UML form. And I have the same issue as in the ODE case. I need also to put some short time or do something just to get the right feature better. Exactly as we always do this. But I need to do that. Then the short method looks like a bit tree. When you do simulations, you see very clearly that there's some kind of initial layer where things are completely messy, and after some time, it looks like everything is just obeying the dynamics of the art. You see some kind of patterns that are complicated at a very short time, because everything is well organized. On this, I will not debate. There is one ingredient that I should add, but how to do with the kind of quasi-linear behavior, because if I just do German formula, I will not close. So I need to add something. There are many ways to do that. One way that is quite obvious, I can consider being estimate. I will explain this in the next program, and not now. Okay. What would be the crucial here is on the next program. The thing I want to explain is how to do that separation. The new ingredient. This. So I go back to the linear equation, and everything that is good, I will put on the side. And then I need to just check that the bad things are aligned with this line, so that I could put them in the S. They have the structure so that I could, if I take derivative. Also, I will use the block symbol loss, everything is not in symbol. But if you start and say, okay, at T equals 0, I have 0 in the spectrum, I will do some to then I will get a vector for the eigenvalue inside and C as well. What I know for C equals 0, I will extend with projector in the way I showed you yesterday in the perturbation theory. Of course, there are things that I will do if C is not small. Then the spectrum is far away from the frequency, so I expect that we get exponential decay. In the same way, it's small. But I'm focusing out the part. It's not decaying, so also for both these things with decay and but I need to analyze precisely is what happens for dynamics of this guy. Now we use by using extensions. We use the best, okay, just to reduce to the D plus 1. Let's start with D plus 1. I can give you D plus 1 and we can formulate this. What are the ways to do that? Yes. what I'm writing is just I can do coordinates so that it does one mathematical problem, then I will go back to the problem. Ah. You know how they begin. First, the Dixie is domestic, so that's the seen before. Or also, the beginning of this thing. We got prime. So the vectors we know for, but are generating generate like in space from 0. And we also know part of the dual thing. So we don't know the one that is in the prime price one. We know the other ones. The other ones that we chosen them to be constant function aligned with just right. Just mean that they are constant equal to an element of the canonical basis of R. This is the thing that we extend. So in particular, we know we know D0 because we C equals 0, U prime is in the kernel, and the image of this guy is a multiple of U prime. Like 11 prime. That's the same private one, it's 0 of U. That's the Jordan block structure of the mentioned. Okay, it's what we got by just taking derivatives along the family along the profile equation. But what I'd like to do is understand what happens to that when I perturb in C. But this is a Jordan block, so okay, in general, I will lose some kind of regularity. It's typically the case where when you look at spectral perturbation, you lose some. And this loss in C is responsible for the fact that you have upside, it's not decaying. So to analyze perturbation, what I should do is something like a blower. In the sense of algebraic geometry, so I need to do some transformation so that in the end I get this thing eigenvalues. I need to do that just to reach the stage where I have this eigenvalues, then I can diagonalize in a nice way, undo the blow up, and see what happens. What should I do essentially? So everything everything where I got 0 for DC, it's at least of order C. Then this guy is at order 1. Okay, so more or less I'd like to multiply this by something small to make it and then divide the others by something large. No, okay, divide by something equal to. So that's then they reach the same size, and okay, and this is a fixed matrix, and everything is fine. To do this, if I want to multiply this by something, I should it didn't change our variable. So if I multiply this by something, I should divide this column by the same. So then I need to understand what is exactly the order of this column. This is what we already know that it is at least of order C. And the discussion is it of order C or higher. So if it were of order C, then what I would do is a scaling with the square root of C. This would be very bad in plenty for plenty of reasons. So this is not happening. Okay, what we need to show is that the structure is giving you that it starts at order C squared. Then you could divide by XC and make everything of order C. Let's see why. But that when I like to understand, then it is what is the order of C. I'd like to show that it is at least of order C squared. And remember that when I do C equals 0 ici, this is U prime, it's in the kernel of F0. And when I do C equals 0, these are constant functions, they are in the kernel of the adjoint of F0. Okay, so when I do the first order expansion, the only part that will remain is when I need to expand this in C. Okay, otherwise it's 0, whether because it's F0 applied to something or because it's this against F0. So I need to just know what happened when I moved C here and I applied it to U prime. Okay, that's what I need to understand. So I need to understand what happened when I vary C. But if you look at where C is in the equation, it is coming from the fact that you replace dx by dx plus ic. And the k variable is at the same place, okay? Because the k variable in the equation is coming from the fact that you have k and there's a k. And essentially what it's telling you is the differentiating with respect to C is the same as differentiating with respect to K. So then I will use the extra parameter I've not used so far. That is the way they also depend on K. So if you differentiate with respect to K, the profile equation, you will get something. My claim is that this is of order C. Equation. Okay. Yes. Give you that. Then belongs to I don't need more detail than that. I just need to okay, if I get that, this is fine. But this is thing I need to plug here. And then more or less I need to plug this here and apply this guy at 0. And so this guy is orthogonal to the range of L0 and it's orthogonal to U prime. Okay, so this will give me 0. And this thing is just coming from the profile equation. And when you differentiate, if you don't differentiate the K part, then you get either L0 applied to something, because you differentiate the U part, or you differentiate the speed. Okay? If you differentiate the speed, you get a multiple of U. So the only way to not get something like this is to differentiate the. Okay. I'll say much more about that. I will use it now. In the way I've already mentioned, by scaling that I can scale with this. Again, what I'm saying by the structure, because it's just giving me trouble, it's also everything. Okay, so what I should do now is then for change of variable. So I've done that, everything is of order C now. So we just divide by C. But when I divide by C means that I'm looking at how those eigenvalues are separating linearly in C. So my assumption about group velocity is that they are separating linearly. So by assumption, I should say delta C is smooth. Yeah, I could always do that for C not zero, but the point is that okay, I'm not putting anything. So it's analytically. The assumption is that delta zero and then I can diagonalize smoothly delta C and go back to DXC and see what I get. Okay, so I can diagonalize. There are things coming from the final dimensional diagonalization. There's still get So you're paying a price. Okay, you are because of the change of variable. There's a 1 over C here, and there's a C back. It's coming from these things. When I go back, so I could diagonalize, but I charge the price. And this is necessary. Okay, in the end, if I have full diagonalization, it will mean that T0 itself will be it's not because it doesn't have to pay. So this is the price to pay. But it's the shape you get when you do the code, but then it'll be more convenient to write it. Say, right one, I want to factorize 1 over C, just group together all things, then I gives me. I just expand and group together, I think with the same exponential, I can get some shape like this, where we need to know. So everything is small here, then you see singularity is on here. And like C equals 0 here, I see that the whatever C was only in factor of Q0. So it's just a multiple of Q prime. where it's coming from, which is useful. Okay, and the fact that I had some T everywhere. Yeah. Guys are not in duality, not quite in duality. You need to get something like this to console this bad factor. So the whole object, the object that is I'm using some singularity only because I want to diagonalize. Everything is movable. And I want to diagonalize simply because in the end I want to go back to the near constant analysis for analysis for multiplication. So for this I need to get scalar equation at my out of zone. I'm essentially done. I know what to do. The only problem for me is that there's a 1/c sin factor, so I should expand a bit to create a 1/c factor, and then I get a good thing that are negated by the diffusively. And I'm only allowed to remove something that is aligned with the group file. But that's good because I know that this guy starts with the prime, so I should remove this part. I will gain a C factor. Like this. Which means that we also have one time and you go to the next time. So reality is really then you forget, I think that SG I will do that. That's the same guarantee in C. There's meaning, but I cannot really say what is the if I take the derivative, I take the derivative space, I just get C factor and then I back space. But if you get time, I will also get some C factor, then it will be this. Okay, I will not explain that all of this. Yes. Then I'm using the splitting of a symbol in the geometry formula. Then that gives me the splitting of the sides. what the possible are and so on, subject that I don't really know how to do that because I mean it's continuous in size, so it's okay, I could try to do something like this, but I don't think this is very common. I don't think but it's kind of a C dependent orthogonality, so I could try to do some kind of orthogonality without transform. And I don't think this is very common. But I'm removing something that is C dependent. And parfois, what is true is that there are plenty of choices. If you want to go to the next stage, which is to describe the dynamics, then you have less stuff, and you have to be better to move and you can try better. So the efficiency and whatever. Exactly. Not in short time, but in long time, it's exactly. And I have some choice here in the speaking. I don't the simplest one to do. So that's not the best one if you want to go. Okay, I've got thing about that. It's like, what is the goal in the description of large time dynamics? More or less, it's go from getting something that is like clarity, go to something that is strong. If you go back to the functional dynamics. And if you look at this formula, it's something there's no block anyway. It's like there's almost no block, it's more like 40 form. You see that the phase itself, it's not really doing something very big, it's doing something that is simply near constant dynamics. So, so the phase itself should obey kind of average dynamics. This is what we put. The phase is not the phase, the average of the phase. The wave number are totally constant with the value, the background wave number. This is what I think of the This is where to find something like the Perverse equation or Perverse near constant equation. Wait. Yeah. It's coming from algorithm dynamics. Right. I had the deepest two dimensional family, and they have only modulated the position of the phi part of the dynamics. So if I want to get a better description, I should also compare to something where K and M part are determined in time and space. Tune the description correctly, but when I remove this, I get something that is getting fast. That's not. It's super science. It's not big. It's not good. The reference solution is something that you know think so it's a traveling wave. Yeah. Profile is doing something that is quite small. Yeah. It's not hyperbolic equation, so it's kind of natural that there are some discontinuities that are not bad. Then I think so for natural, it's quite to think about the stability of the things. So of course, there are this coming from the fact that I work on the fact that it's not too bad. Strangely enough, the older result and the older the strong sense of this kind of topic, they are very good. It's not so complicated. But and I'm taking this kind of object mostly because in a way this is the simplest one for discontinuous space, but it's also even if I look at among the more general tests of things, turns out that when you need to do complicated things for two forms, then the standard way to do the complicated thing is to artificially consider it as something that is completely somewhere on the boundary, and then conjugate each part to a constant. So even the smooth forms, when you need to do hard analysis of it, you try to conjugate it to something that is equal constant. And I'm saying for front, but that is also the same, even when you have a solitary vector, the same inset on both sides. You also do the same when you need to do something complicated. If you split somewhere, you do conjugation for piecewise constant. It's twice the same constant. It's very split. The conjugation is not the same. Maybe something. So something I would save me some work to consider something that is already piecewise constant. Just not need to do the first step of conjugating to something that is piecewise constant. Yeah, so of course there are conditions for this to be a solution. Want this to be a weak solution, then we should solve the equation in the smooth parts outside of zero. So it just means that plus and u minus should be zeros of g. And then also, since this is discontinuous, when you take derivative, you could create a Dirac mass. Okay, so you have to be sure that you're not creating a Dirac mass. And the equation taking this is exactly. Okay, so if you look at discontinuities moving with speed c, if you write down what this means to have no Dirac mass in the equation, it's exactly that. This is a particular case of pointing equation. And I need to add conditions. Well, I will not discuss too much. Let's say I'm assuming them in some strict sense so that when I perturb it, they remain. This includes something that I will discuss later, which is some kind of price probability. Why do I assume this kind of thing? Essentially because I will take as for granted the local in time solving. Like I could do for ODEs, like I could do either a fixed point argument that gives me resistance or do a continuity argument where I already assume Cauchy-Lipschitz. Yeah, I will rather use the continuity arguments. I will already use the result that tell me that for short time things remain like they are. Then I just need to prove that I can continue forever and get a good control. And these are the conditions that ensure that you get some kind of stability for short time. And when you perturb, you're not breaking everything. The structure remains the same, meaning that you have one discontinuity. And so, if you're not familiar with hyperbolic equation, it's not always the case because the notion of solution we are using is kind of a vanishing viscosity notion, and because of that, there remains some regularization properties in the equation. For instance, there are some discontinuities such that if you try to put them to the equation as initial datum, they disappear instantaneously. Okay, the solution becomes continuous. Okay, so you need something on the discontinuity to ensure that it's not like this. It remains like one discontinuity. Okay. So I will not take too much this at reference for that. The local resistance part. Yeah, I should say. Matter for me that I need to control that the solution keeps existing, so I need to know what is the quantity that should blow up if the solution stops. Okay, and is it W1 infinity? Or this way the one. There's a book for that. The content that comes from that is name that made the result I'm using is of course it was Maida and then yeah. Mostly when he was in Iran. I mean, that's quite strange, but I'm looking at the one-dimensional case, but I'm counting multi reference. It's mostly because the point of view of trying to control piecewise move the construction is something, somewhere the only one we have in multi and it's much more developed. So in the 1D case, we have a good notion of infinity solution. So okay, so I'm not to look at this. But if I want to get some kind of control and stability, I need more than just an infinite. I need to get some notion of what is going on with regularity and discontinuity and so on. And this is something that is being much more developed. But here, I don't know the right account that is doing the thing I need in the 1D case. And we also, of course, do is take a density equal to 1. And I'm taking it for granted mostly because it's these are not short codes. And they do not contain exactly the result I need, but by doing some variation. So for instance, one thing they don't do, but it's usual that they don't have a source term, like there's no G equals 0. For short term, that doesn't matter. For long term, that does matter. And then you have to, modify the proof by including some G almost everywhere, but okay. So this way of looking at the problem makes it somehow an initial boundary value problem, and the free boundary. And therefore, when you need to solve it, more or less you are imposing both initial datum and some kind of boundary condition, and then you need to compatibility condition if you need to propagate regularity. Because you're fixing something here, something there. If they are not compatible, instantaneously you're creating some problem. Like you write things that need. So then I will also have this kind of discussion. I will hide this kind of discussion. I think that I'm assuming compatibility conditions so that I get local in time persistence. The good thing is that the result, they show that the compatibility persists. You just have to assume it at initial time and then it propagates. Everything is fine. There are at least two easy ways to assume that the compatibility condition without writing anything. The first one is to force perturbations that are far away from the discontinuity. Then you're not perturbing what happens near the free boundary, so of course it's compatible at any order. The other way is to say, you start with something that was already defined in the past. And then because compatibility is propagated, it derives with the good compatibility condition. Right. Now we're back to something where there is essentially only one variation somewhere. And so it's not like the periodic case, so you have infinitely many positions to synchronize. You just have one position to synchronize. And so it's possible to have just 0 as something isolated and then a gap. And so I will assume that I am in this situation. So it's very much like the stability of the periodic solution for all these we've seen. And then I will also be able to just use orbital stability, just for synchronizing or something with a phase that depend on time. Something that is not obvious is what is the linearized problem and what is the spectrum. At least I will explain this. So we work in H2 just because of that. I mean, I need to something that control W and infinity. I will work in integrals of H2, like minimal thing. Okay, this is. But there's something like that. I can do plenty of those. Merging is very different. One year, on the top of the system, there are different for UTD, it's not the case that particularly for general system and UTD, the only thing for which LP is sent to LP time by the linear evolution is equal to then depending on and this you already have when you work such a way evolution. So for already true for the equation in UTD, the only thing for which you can LP to LP is equal. You don't say how to get the data would be case. So it's just coming from an integration of type. Type exponentially decaying, the type 1, sorry, type 1 is exponentially decaying. So you can just define type infinity as being type 0 with the integral from 0 to infinity of type. It's very implicit, we don't need to care about that. As soon as you have some integral data here, you get some. Oh, but it is one of the. You don't have simply phase, then you can do some kind of logarithmic change. It's called modified scaling like this. And it's just coming from fact that when you do the side prime indicate that one works. Then you can integrate with the total t from time. But if you never see the side of the code, then you can see side prime. Plenty of comments about that. Yeah, there's no choice in the phase. Because I'm using the phase for two things. One is to get the good large time dynamics, fixing the position. But also, since I'm working in a piecewise smooth topology, and when I do comparison, I need to fix the phase exactly. Okay? So I'm comparing two objects that have a discontinuity. I need to fix the discontinuity at the same place before doing the comparison. There's no choice for that. I'm using the word particle stability because that's the standard word of the stability. But if you look at some recent papers in the field, sometimes people just say stability. But that's the same thing. That's the difference. Yeah, because even for short time, you need to increase the shape. But that depends on the topology. There are some topology that don't see so much that you're completely correcting the position. You want to improve the topology you want with, then you have to position. There's been essentially only realized very recently that you could plenty of things to do that. The useful power, I see better, G1 with that doing this kind of thing, getting better result by getting correct page. I should say that the assumption I'm making is the simplest one, but it's not general. Okay, so if you take a system in general, you will not have to get a spec for that for something that is piecewise constant is exceptional. This is not regular, but we also know how to do more complicated cases now. Something that is not exceptional is the case where you have something with a single discontinuity, but not piecewise constant. Basically, when you have a variation, other variations, and it's even more robust if you are allowed to move away to play the show. So the situation where your background rate will not be piecewise constant, it's piecewise regular, and you are using the way to play the gap. This one is quite good, and it can be done with the same kind of elements. In the papers out. It will be essentially what it's done. The external guidance you need are the one I mentioned before, to be able to do the complication of sort of thing in the case of full form. That's possible. By weights, the spectrum depends on the space move, right? Wow. You can use some weight that you keep move part of it. Let's break the gap in the equation and get that. One more comment, and the paper is, I think, quite readable. Do not say the same thing for me. In particular, we've written things in starting by doing first the stability analysis of just constants, exactly the same ingredients. And then constant on a half line with boundary conditions, then okay, moving to the flow shock thing. So it begins slowly difficulty. And but for the constant, already for the constant case, I think it includes some new results. I mentioned that. I think because we are doing a really accurate result, that we are assuming only spectral thing, and then we are able to get something at the nonlinear level. And that we are, this is not a standard way to do. Okay, like it gives you most of the time proof that they are more complicated, but then the result is sharp. And they are more complicated than just doing energy estimates. Okay, so usually, if you can conclude by energy estimate, the proof is quite short, but it's far from being sharp. Okay, the only thing you can say is that when you cannot conclude, it's like okay, you cannot conclude. Don't need anything. So in this case, when it stays in a strong way, like you have some spectrum on the other side, then you expect that you will get some stability. So in the constant case, I think the available result, we are only dealing with the case that you can do with an energy estimate proof. And I'd like to so what are the standard results? Essentially about the constant case, there's a book by Litzatien that is global, classical. There are many books. I'm just writing the beginning of the book. There's also that's these are the standard things for this. Like to give you an example of things that are not covered by the energy estimates. Yes.
So just to understand, there is the case that you have this minus alpha 0 because you have some dissipation in
the G part. Yeah.
Okay.
Yeah.
Thanks.
And what I'm saying is that
and it's a CDS.
No, not at all. Really not. So in the case where G is not full rank, then this is the case where you would need to use some ways to create some dissipation and to create a gap. Okay. So in most of systems, the G is not full rank. That and some of the equation, but not all of them. I'm saying that if you use a weight, you can still create a gap in many cases.
So you mean use the weights?
The special weights just to
way
create a gap. Yeah, exactly. Yeah, and if you have a G that is not right, then you will have 0 in the spectrum, and if you are looking at something that is very constant, there will be some touching. So you can move this touching by using it. And then you can do an argument like this. And I'd like to finish by giving one example of a case where okay. I think it's surprising to many people. At least it was surprising to people. It's a 3x3 case, constant coefficient, where you get exponential stability, but we cannot get it by standard energy estimate. It's constant coefficient. So of course, if you do advanced energy estimate, you could do it. So it is in the vector combination. A, E, and there's an epsilon or what I'm my claim is that for this system, you get exponential decay. The things are very bad for energy estimate. So you should compare with the Lyapunov theorem. Okay, the proof of Lyapunov theorem I was mentioning, I've given you is by UML formula. But this is one proof. There's another proof where you do, okay, I do something that is dissipated at the linear level, quadratic form, and then I check that this is also dissipated for the non-linear term, the perturbation. So this is something like an energy estimate. So there's a proof of Lyapunov theorem by energy estimate, essentially. And it's so that tells you that for ODEs, the proof by UML or energy estimate, they are covering the same basis. So I was mentioning that it's not the case for PDEs. This is maybe the simplest case where you can see this. That's the case for equation with scalar equation for system of two equations. It's well known from people doing hyperbolic equation that these are non-generic. Okay, the generic situation starts when you have three situations into dimension 2. I'm using three equations here. So you get exponential decay, but things are bad for energy estimates. How do you do energy estimates? So the first thing you think is, I will do a scalar product with essentially a U, but I'd like to get rid of dx, because otherwise I'm losing derivative. So for this, I need this to be symmetric, so that's not in the integration by part, it's gone. But there is some choice. There are some choices in the symmetrization. And then I look at the zero order term and see if I can get something. And then I'm claiming that in this case, for any sigma symmetrizing A, what you get on the other side is that, meaning that the real part of sigma B has spectrum with positive real part. So it doesn't mean that you have instability. I've said exactly the reverse, that you get exponential decay. I mean that when you start to do the symmetrization thing, and then if you check if you can get something, then it looks like you have an instability. Okay, so you need energy estimate giving you some growth, some fake growth to get. Okay, so this is it. Of course, you could do more things that are more complicated, but at least the standard way to deal with these things are when you completely lose. Maybe I can say that most of the theory it starts with assuming that this is non-positive, and then trying to check how to go from that to get some decay. Like you're saying that it's not growing, and then you're trying to do some tricky things to get decay. I'm saying in this case that in this simple case, you start with growth. Then there's no trick. You can do nothing about that. You have to change your rate. You can do more advanced energy estimate. It's possible because it's near constant analysis, but it will be not okay. It will not be simpler than the spectral proof. Even for such a simple example, if I perturb this a little bit at one your level, then I need to teach something better than that. So yeah.
Any questions? Maybe just to understand this, I think I have. So anything related to take our Shimashi to the strategy work here doesn't work, let's say.
Yeah.
No?
Yeah, that's true. I mean, also, so
even if you take just the symmetric part of B, you still have this property that the spectrum is.
yes. I mean, it's really coming. Okay, I will discuss Kawashima next time. Okay, some Kawashima things. So the thing that I am pointing out is that in most of results there is some hidden assumption at the very beginning that ensure you that if everything is fine at high frequency, everything is fine everywhere. And so in this case, we are not in this situation. Yeah, this is a case where you get some high frequency damping. I will use them in the proof. I already mentioned. I will explain how to get that. But you cannot get some damping in low frequency or mid frequency. Okay, so it's because there's nothing that tells you that when it's good at high frequency, it's good everywhere. And the thing that is robust that you can use everywhere all the time is high frequency damping. And then you need to complete it by some. Okay, the way we do this thing is by you complete it by UML formula and linearized analysis, and you have to go into the details of linear analysis, but you lose the derivatives, and the high frequency just recover the derivatives, and this one is robust. And in the high frequency analysis, you find the Kawashima condition, a part of it, okay, without the symmetry assumption that you assume at the beginning that will give you some extra kind of argument to do the energy estimates directly.
So let's say, in the high frequency regime, this becomes say DC, but in the sense of
exactly. This is exactly that. So part of the proof of the result here is to show that if you have a spectral gap for a linear operator, then you have a good structure to do energy estimate for high frequency damping. Not the full thing. Okay, you could still get some instability in the low frequency, but okay, have some good damping.
Okay, so if there are no more questions, I think we can thank Luis again.